I'm back working on the Wren computers. If you've been following my series of videos on these machines, then you'll know that I've been working on 3 separate machines, and 2 of them I've now got up to the point where they will boot reliably from the floppy disks that we've made up. But this 3rd machine is really been a bit of a headache. It kind of worked, then it didn't work. It works for a while, it crashes. It's operating in a very flaky manner. So I suspect there's a timing issue on the board somewhere. We've got some failing components on here. I've already swapped out quite a few components. I'm not quite sure what happened to this board, but quite a few of the buffers had failed, some of the counters and timers had failed, the floppy drive controller had failed. So it looks like it's had a power surge issue at some point, and there's still obviously a number of faults. I think there's more than one fault on this still, so I need to try and track down what it is. It's been about a month since I worked on these. I've been drawing up some schematics from some original material that one of the original developers was kind enough to give us access to, and that should make life a lot easier. Especially with this sort of fault where it's not just as simple as it won't work and it does the same thing every time. This is kind of fairly random, so it was going to be very difficult to track down. In order to try and make progress with this, what I decided to do was to make the problem worse. And what I've done is I've modified the supply in this particular chassis. I've lowered the 5-volt rail by a couple of 100 millivolts, and that will have the effect of making this issue much worse. If it's noise and failing ICs and thresholds aren't being met for the proper switching characteristics, then lowering the supply voltage normally has the effect of exacerbating any particular issues that the board may have. So I think that's most likely going to allow us to make some progress with this. So I've done that, and now we're effectively back where we were in the last video in this series. So that was Wren board number 3 part 7, so this is effectively Wren number 3 part 8. So I'm running this now at about 4.8 volts on the 5-volt rail, and if I switch the Wren on, then we'll see it will go through part of the self-test, and it's now failing at test step 2, and that is the video RAM. Ignore the fact I've got these video RAM chips removed. This particular part of the test that's failing is testing these 2 SRAMs, and these are the character RAMs, and this is where it's currently failing. But because this is running the built-in self-test, there are other things going on, and what I really want to be able to do is to test these in isolation. So what I'm going to do is connect the fluke, and we'll be able to address these memory devices in isolation, and we can then ignore most of the rest of the board and start trying to track down what's going on. When I had this running at the full 5 volts, it would fail at random points in the self-test. Sometimes it would fail at the test 8, which is the checksum test for ROM in bank 8. Other times it would fail test 1, which is the main system RAM. But bear in mind, it doesn't do these in order. It doesn't test 1, then 2, then 3. So test 8 is, I believe, the first test that it carries out. In fact, I think it's the second test it carries out. I think it does the main RAM first, and then it does the checksums on the ROM. So it hasn't at that point gone through test 2. So I think what we're doing here is we're getting a failure reliably now at test step 2, which is actually, I think, about test step 4, so it's very confusing, but it's failing at the test for these 2 SRAMs, and it's doing that reliably every time. The other thing that we're getting is a couple of these buffers are getting very hot, and one of the advantages now having proper diagrams, of course, is that it's much easier to follow through and see what's on a particular bus. And in fact, what I did when I drew the diagrams is I drew them in such a way that they were useful for this type of fault finding. So, for example, common buses I've identified as actual bus lines, and this means it's very easy at a glance on the schematics to see what devices are connected to a particular data or address bus, and that means it's much easier to identify where contention may lie. I've had a quick look through this board and it was still running at full voltage, and there is significant overlap on the enable signals going to a couple of the buffers, and that means it's not the buffers themselves that are at fault, it's the glue logic is misbehaving somewhere, because the overlap should be minimal, but it is quite significant, and that's I believe what's causing this weird operation. But what I need to do first is try and pin down some of the faults that exist, eliminate those, and then hopefully as we work our way through we can identify any timing issues, work our way back through the glue logic to find out where those issues are originating, and then get those devices replaced, and hopefully we can resolve the problems with this board. So next step, we'll get the flute connected and then do some manual testing on these SRAMs. Okay, I've got the flute connected using the Z80 pod. I'll power the 9010A up, power up the Wren. The Wren will not, of course, run at this point, but I will press reset just to make sure that as many of the circuits as possible are properly reset. Now, one of the first things we want to look at before we start doing any memory testing is to figure out where the memory is mapped to. And one of the important pieces of information that we managed to get was the memory map. Now, I had reverse engineered most of this anyway, but it is nice to have the original document so we can just confirm that what we were looking at is indeed correct. And the memory we're interested in here is in bank 8. Now, the first part of bank 8 is the EEPROM, so that's one of the ROMs, and then we have three more banks of, or three more areas of RAM. We've got two of the DRAMs, the video DRAMs, are for what is referred to here as color RAM. Another two of them are for character RAM, and then we have it's screen RAM, and then we have 4K of character RAM. And it's the character RAM that we want to test first. So as you can see, I've taken out the 16K video chips, and the two SRAMs, which are these two devices, are the ones that we want to test first. So I've taken these DRAMs out just to make sure we're not getting any conflicts or crosstalk between them. Before we start testing, we'll just confirm that we can successfully switch banks. And with the Wren, it's quite a nice layout they've got for the memory map, in that it's divided into banks. Each bank can address Z80, of course, up to 64K of memory space, and so that gives us quite a good addressable memory space. But to switch between the banks, we need to write to in-out port 0, and if you're interested, this is where this takes place on the schematic. So we have these flip-flops here are where the bank selection is made, and then this small circuit down here is what's responsible for mapping the top 4K of RAM into all banks. So if we look at the main memory, it's 64K. It can be expanded, but the top 4K in all banks is actually the top 4K of this memory. And as I say, this part of the circuit is what's responsible. It's just really taking address line 7, and it's controlling that whenever it's appropriate to map that bank. So we need to make sure we select the correct bank before we start doing the test. And as we can see, if we look at the memory map again, we're looking for bank 8, so we need to make sure that we're in bank 8. Now the machine in theory does default to bank 8 during a reset, but we will check that to make sure that that's the bank it's currently set to. So looking at the schematic, it's these two devices, so that's U29 and U30, and the outputs are pins 5 and 9, and if you look at how these are arranged, when they're reset, the first 3 flip-flops outputs default or reset to 0, and the last one is reset to a 1. So if we check those, so if we look at the first device, so pin 5 we can see is low, pin 9 also low, and if we check the other device, we've got pin 5 is low, and the last one should be high, which it is. If I now try writing a different port value, so I'll try setting the port to 0, we should see that line drop on the scope. So I'm going to write the port 0, and I'm going to write a value of 0. And as you can see, that line drops, and I'll try setting it back to 8. So as you can see, we can indeed select the correct bank, and the latch and the flip-flops seem to be working the way that they should be. So what I'll do now is move the camera so that you can see the float screen, and then we'll test these two devices. So we've got the correct bank set, and we now need to try writing data to those devices and reading it back to see if it's correct. Okay, so looking at the fluke and referring back to the memory map, it's this top character RAM we want to test, and we can now ignore the 8 at the beginning. That's the bank number, we've got that set. So we want to test the memory address range from C1000 to CFFF. There's a number of ways we could do this. We could write a script, which we probably will do in a few minutes. We could write some code to upload into the Wren, which I may also do. But we'll take the easiest route to start with, and we'll use the built-in RAM test function. So we tell it where to start from, which is C1000, and we want to go up to CFFF. And straight away we have a bit error in the data that's being read. So what we'll do now is try writing a value to one of the memory locations in that range. So if we start at C1000, we'll set a value of 55, we'll read that back, and the value that's read back is 75, so that's incorrect. We'll try a different value. We'll read that back, and this time it's read back correctly. So we'll try writing the original value back again and see what happens. And we're getting exactly the same result. So it looks like we've got a bit error, so we'll try and figure out exactly which bit this is. So we'll try writing a value of 0. We'll read that back, and we're getting a value of 20, which is what the self-test, the built-in RAM test, showed us. We'll now try setting this to FF and see if it is a stuck high bit, and if the other bits can be toggled. And indeed it is, that one bit seems to be stuck high. And if you work out how a value of 7 hex relates to a value of A in hex, you can see that indeed it is a stuck bit. So we'll just confirm that one more time. And indeed that bit is stuck. What we'll do now is we'll try the next memory location to see if it's a bus issue or a RAM chip issue. So we'll try writing to C001 and we'll write the same 0 value to that, and then we'll read that back, and we're getting exactly the same issue. We'll just try one more address. So this time we'll write to C100 and we'll read that back, and as we can see it's given us the same issue. So most likely this is a stuck bit on the data bus. So what I'll do now is go back to the board. We'll actually scope this out. So what we're looking for here is an error on the data bus, and it's bit 5 that we need to be investigating and see why that's not toggling. We'll start at the RAM chip, see if there's anything going on there, and then we'll work our way back through. Chances are it's a bit that's failed on one of the buffers, but we'll have a look at the board and see if we can figure out what's going on. Now this is where the fluke can come in very useful, because what we can do is set this to loop, and when it's looping it's just now continuously reading. In this case it's just repeating this command, so it's reading from that address, and this will give us a good idea as to what's going on. And of course we could then do or set a value of FF, and if we need the data lines to all be toggling high, then we can see whether they're all toggling or if there's an open circuit or a faulty buffer. So looking back at the board, if we consult the schematic, these are the two memory devices that we are testing at the moment, and they communicate to the processor through these two buffers. So one is in the write mode and one's in the read mode, and we need to see which one of these is at fault. So we don't know if the value is incorrect because it's not being written correctly, or if it's not being read back correctly. But what we'll do is we'll start off by seeing which of these two devices is in theory being addressed. So we'll look at this device first. So the pin we're interested in is the output enable pin, or the chip select pin. So pin 1, and that's this device. And what I'll do is I'll start the fluke continually cycling, and as we can see on the scope, that device is being addressed. So what we need to do now is to see if bit 5 is supposed to be a 1 or a 0. So we know that the value we've written into memory should be a 0. We just need to see what value is being read out, and we could do that by looking to see what the value on that pin is at the point when the device is being enabled. So that's what I'll do. The bit we're looking for is that's pin 6. So we need to monitor pin 6 on this device at the same time that we look at pin 1 and see what the two values are. So we can see the device is being addressed, and we can see that the value there, it's kind of trying to go low but not making it. It's just a bit of noise, and now and again it's gone low there now, and in fact the fluke has just successfully flagged that as a read. So it could be we've got a dry joint underneath this device. So let's run this test again. It is now reading as 0. So we'll test that again. I'll put it back into loop mode. Okay, it's now reading correctly, so it could be that we've got something amiss with the connection onto this device. So what I'll do, I'll take the board out, turn it over, have a look underneath and see if we've got anything going on underneath that IC, or it could be something in the area or even somewhere else on the entirely on the board, just me moving the board around. But I'll trace it through, see if I can find out what's going on, and then get back on camera and see if we've made any progress. Okay, well, as you can see, the Wren will now boot up. I don't think the board is fixed by any stretch of the imagination. I think there are many more faults on this particular board. But I did find an open track on bit 5 going to the buffer we were looking at, and it just wasn't connected to the main bus that it was supposed to be feeding data onto. It was just another of the through-hole wires had broken somewhere internally. But once I'd tracked that down and repaired it, the board is now booting up again, and it is now booting at full speed as well, so this is at the full 12 megahertz, so it's possible this particular issue was one of the main faults. Now it's fixed, I need to start going through and looking at the other issues this board has. As I say, I still don't think it's properly resolved yet, but certainly it's a step closer. And one of the typical faults I've been finding with these machines in that they do seem to have quite a few board issues, especially on this side of the board where the battery has leaked and contaminated the board and caused some corrosion. Okay, so as you can see, the machine's still not happy, it's still doing strange things, but it is now booting, so that's a step forward, and I'll try raising the supply voltage back up to the full 5 volts and see if it's any more stable. What I can now do is plug the floppy drives back in and see if it will boot up to the operating system. Okay, so I've got the floppy drives plugged back in. We'll try booting it up and see if it still gets through the self-test. So it's gone through the self-test. It is kind of attempting to read the floppy disk, but as I say, this is a very flaky board. I think there's still a lot of faults with it, so it hasn't succeeded booting from the drive. It is trying to drive and read the disk, it's just not making much progress. But this does not surprise me. This has been a very troublesome board, and I suspect there are still a number of issues with it that need to be resolved. Okay, so as you can see, it's kind of working, kind of not working, and this has been the issue with this board. It's making small steps forward, but I think there are so many issues with this board. I think it's probably still worth repairing because the rest of the machine is in such good condition, but I suspect there's still quite a few devices on this board will need to be replaced. So the next step is to go back to where I'd left off before we had this most recent issue of not passing the self-test, which is that some of the buffers are getting very hot, and I think that the access to some of the data buses are overlapping from different buffers. I think more than one buffer's been put onto the bus at once. So what I'll do next, or in the next video, is we'll hook up the scope to the control lines for all the devices on each of the various data buses, and see what overlap we're getting, and then try and figure out exactly why it's doing that. Chances are there's a failure in the glue logic, or it's possible that one of the in this board, because the clock frequency is so high, so turn it off because it's obviously not happy. Because the clock frequency is so high and it's really pushing the limits of some of these devices, it does require wait states in some of the access to some of the devices, so it's possible that there's an issue in some of the memory or refresh timing that needs to be looked at. But at least now it's sometimes passing the self-test, so it's getting a bit further, but the next step will be to start looking at the various timing and seeing what's going on.